I'm really sorry about that. I just had some issues with getting set up today. And yeah, that's not great, but here we are. Cool. Let's get started now. Um, cool. So, real quick, how was everyone's weekend? Anybody have a good weekend? Anything out of the norm happen? Anything fun? No? Nothing interesting happened for anyone? Wow. Okay. Well, I guess I'll just go ahead and share my thoughts as well. So yeah, right. Yeah, that sounds about right. Everyone's like, we were in quarantine and we did nothing different. Yeah, sounds about right. Zorays, you went outside? I hope you did that safely. Okay, yeah, for a walk. Yeah, so I am right now trying to figure out how to get my exercise in and how to get my outdoor time in. Both of those are going to be super important. So trying to make sure that I can get that all taken care of. So right now I'm trying to figure out like, hey, what are some parks near here that I can at least like drive to? Because you can't really take Ubers anymore. You can't really do anything really. Building roofs. Unfortunately, my building's roof is closed because they don't want everyone to be doing that basically. So that's been interesting. So yeah, I think next weekend my girlfriend and I are just gonna drive somewhere to like some park and just take a nice long walk for like multiple hours. And yeah, in-home workouts have been super important so far. So like I've been adjusting how I do workouts. So that'll be fun. Yeah, and then yeah, walks to the park are going to be exercise, but the problem is when you live in Manhattan, there's only one really big park here, which is Central Park, which is now a hospital, so it's not going to work too much. If you have suggestions, please tell me any parks that you like in the area, and I would be happy. I would be so happy if you could give those to me. Please tell me. Thank you. Cool. And then the other thing over this last weekend, I helped organize, I got my guest lectures, everything that worked and whatnot. Um, so that's been fun. I organized tomorrow's lecture. Again, I really recommend you come. There's going to be, if you missed all of my announcements and emails, there are going to be 5 total guest lecturers. I mean, including me, of course, but there's going to be 2 lecturers from Facebook, 1 lecturer from Uber, and someone from Google. And it's just going to be an open Q&A session. I really recommend that everybody come. I think that would be, I think this is going to be one of the coolest lectures, honestly, and I really recommend that you come. Awesome. Let's get started with today's lecture. So today we're going to be talking about A-star. And I know that most of you, if not all of you, have already seen this A-star algorithm. So real quick, Alt-Y or Command-Y to, Alt-Y or Option-Y, raise your hand if you have seen the A-star algorithm in a different class. Okay, a bit fewer than last time with Dijkstra's, but still a decent portion of the class. I'd say about half the class has already seen it. Okay, you can stop raising your hands. I will lower everyone's hand automatically. Cool. So A-star is another one that a lot of people have seen. So again, we're going to do the same thing as last time. You're going to get to teach at the end of this class. And if you teach, you don't have to do the daily quiz, just like last time. And this time, and again, 2 people will not come up. Sorry, that is an artifact from my old lectures. So no more coming up. We'll each teach A-star. And I will volunteer you to help teach. So make sure you're paying attention. I will help guide you through it, and it's going to be a supportive exercise. I'm not going to try to put you on the spot or anything like that. Questions to ask yourself just in case I call on you, are going to be, how would you describe A-star? what key points would you reinforce, and how would you teach this to a large group of students? And if you choose to do this, then again, this will count for your in-class credit. Rushali, you said that A star is not fun. Hopefully my lecture makes it a little more clear. And we are going to basically be running through the exact same algorithm that we did last time and try to teach A star in that way. Cool. And then if something's not working, just give me some feedback. Tian, what's up?
I see that in the syllabus it
Hey,
says
Tian, we
that,
can barely hear you. Your volume is very low.
can you hear me any
Oh,
better?
wait, sorry. I'm dumb. I didn't have my headphones in. Go ahead.
Hey, yeah, so I was looking at the syllabus and it says Dijkstra's. So is it like incorrect, the syllabus?
Yes, the syllabus, the actual subjects are slightly different now because project 2 is going to be due next Monday, basically. So I wanted to make sure that we have, or I think it's due next Monday. Don't get scared if I have the wrong date, but it's due sometime next week, and I want to make sure that you have you've seen Dijkstra as an A star because you're going to use both of them in the actual project. So we did a little bit of reshuffling, but in 2 weeks, we'll be back on schedule with what the lectures say they are.
Oh, okay. All right. Thank you.
Yep. Cool. So just and by the way, Dijkstra's was last Wednesday. We covered Dijkstra's. And if you haven't watched the lecture, I strongly encourage you to go to my YouTube and watch Dijkstra's there. Cool. So going back to Dijkstra's, why can't we always use Dijkstra's, or why don't we? There are some cases that we see where processing every node before finding a target doesn't really make sense. Most cases, we don't want to process every node before finding our target. And even on paths that go away from the destination, we end up having to process those. So imagine a world where Uber, for example, needs access to the entire graph. So what does a graph look like in the world of Uber? It might look like every single intersection that exists, every single point where someone could get picked up. Imagine if Uber needed the entire graph of the entire world in order to connect you with some other Uber pool rider. That would suck. That would be so inefficient. That would take so much processing power. And that's really, really bad. That's what happens with Dijkstra's. Even though Dijkstra's is a greedy algorithm, it ends up processing every single node so that we make sure that we found the optimal path. So Dijkstra's is great. It's better than DFS, for example, because it does provide the optimal path. However, the way that it does that is very, very inefficient for huge graphs sometimes. So that's why we're going to talk about A star today. A star is another SSSP algorithm. So if you don't remember what SSSP means, it's the single source shortest path. So we have one source node, and then we're going to expand from that source node to find a particular path, the optimal path, towards a destination, or in some cases, all of the other nodes in a path. The most common application of this is going to be towards a given destination. So again, imagine Uber pool. Like, we're not going to necessarily look for the shortest path to literally every other point in the world. Most of the time, we're going to find the shortest path to a single destination that we care about. So this is another SSSP algorithm, and it's a very close relative of Dijkstra's itself, but there's a slight tweak to it, and we'll go over how that works during this lecture. So the idea here is to use a heuristic. So this is going to be a very, very important concept. So we have, in Dijkstra's, we use the information from the destination about the distance from the origin, but here we're going to add something. Here we're going to add the actual heuristic of the remaining distance. So that's just going to be an estimate of how much further we have left to go. So we're going to use a heuristic to figure out, what is probably the path that we should explore next? The ones with lower heuristic values are probably going to be the paths that we think are more promising. So let's say that I can get to Long Island from here in a mile if I take, I don't know, Fifth Avenue. But it's going to take me significantly longer if I take Sixth Avenue. It's going to take 2 miles. Then, and these are just estimates that I have in my head for whatever reason. Maybe Google Maps has given me these estimates. Then which path should I explore? I should probably take Fifth Avenue because that's the one that is faster. That's what I estimate is going to get me to my destination faster. A-star is doing the exact same thing, basically. All we're doing is looking at the information that we have, estimates that we have about how to get to our destination, and using that to explore the path, explore the different paths in a specific order, not just some arbitrarily random order, which is kind of what Dijkstra's does. So A-star, the beauty of A-star is that it always generates the optimal SSSP, just like Dijkstra's, but it does so in the most efficient way possible. I don't have the math to prove this, but I'm not going to go over the math to prove this, but I do have it accessible via a URL. So if you're interested in learning a little bit more about the mathematics behind A-star and why it's always optimized, just let me know, give me a ping, and then I can share the link. I'll probably share it in Slack right after this lecture or something, because I actually think that's really cool to be able to prove that this is the optimal algorithm. As usual, don't forget, you can always raise your hand to ask questions. So Alt-Y, Option-Y, just raise your hand in order to, if you have any questions that come up. And I'm going to want you to raise your hands to answer this question anyway. So as usual, why do we care? Why do we need A-star? Why does it have to be optimized when we already have Dijkstra's or DFS or other greedy algorithms that can help answer our question? I kind of answered this a little bit, but let's re-answer it just for fun. Matt, what's up?
So A star, we care because it always give us the optimum path to the goal state.
Okay.
Meaning that, for example, let's say DFS or BFS, like we might find the path within the specific, let's say, the starter point and the end point. But in this case, every time we make a move, we always optimize to the best solutions every move we make to the destination.
You're right on that. You're right that it's better than DFS or BFS because it finds the optimal path. Why do we care, Matt, about A-star versus just using a regular Dijkstra's algorithm?
I would say let's say Dijkstra, for example, if we have a negative weight, we might not be able to use it. But in this case, considering that every time we move forward, we're always going to consider the distance from when we add to the destination. Regarding the weight, either if it is positive or negative, always going to give you the optimum path.
Okay.
To my understanding, yes.
From what I'm aware, I'm going to double check on this and get back to us on this, but I'm fairly certain that A-star is not going to be able to operate for negative weight edges as well. I might be wrong on this. For those of you who have seen the algorithm before, let me know if I'm wrong on that, but I'm pretty sure that A-star won't work on negative weight edges either, on graphs with negative weight edges either. However, that being said, the huge advantage of A-star is that we will always explore the best path. It's never going to meander into the wrong path unless our heuristic doesn't really make sense or whatever. But if we have a good heuristic that makes a lot of sense, and again, our heuristic is just an estimate of how much further we have from a certain node to the destination, if that's right, that this will pretty much always give you the optimal path, and it'll do it really, really quickly. Tian, I saw that you raised your hand. Did you want to say anything else?
I just wanted to answer the question.
And did you want to add anything?
No, not really. You guys got it all.
Cool, thank you.
Mhm.
Awesome. So why we care is, again, A star finds the optimal solution in the fastest possible way if we have an admissible heuristic. I'll go over what admissible means pretty soon. The other reason we care is this is the literal algorithm that a lot of companies use to solve SSSP problems. For example, DoorDash, Uber Pool, Google Maps, anything that has to do with like a source and a destination, you end up using A star a lot of the time. The other common algorithm that we will use for this is going to be Floyd, I believe it's Floyd Fulkerson, and that's going to be an APSP problem, or all pair shortest path. So that's going to be the shortest distance from any node to any other node in the entire graph. Again, I'm pretty sure the only constraint is no negative edges, but this usually isn't a problem in the real world. Like, what is a negative edge going to represent in the context of a map? Probably doesn't really make sense. So we're not really too concerned about that constraint, which isn't a problem either. And then if you do have negative edges, just as a side note, you can use something called the Bellman-Ford algorithm. And the Bellman-Ford algorithm is another SSSP algorithm, but it deals with negative edges. So negative edges are taken care of by Bellman-Ford, and it doesn't really have problems with that. The trade-off, of course, is Bellman-Ford actually ends up having a lot worse of time complexity. So if you are, if you don't care about the negative edge constraint, then you probably want to use Dijkstra's or A star. But if you do have negative edges for whatever reason, like whatever your application is, then you want to use Bellman-Ford. By the way, we're probably either going to go over Floyd Fulkerson or Bellman-Ford towards the end of class. We have 4 lectures towards the end of class whose topics are still TBD. I'm probably going to ask a bunch of people what they're interested in learning. Unfortunately, I can't do a ton more guest lectures or anything, but I can do more mathematical algorithms that we are more curious to learn about, and they're going to be much more advanced than some of the things that we've seen so far. Cool. So the A-star algorithm uses certain terminologies. Like I said, we use the heuristic there, and the heuristic in mathematical terms is defined as h of n. So we'll say h of n is the heuristic here. And then in these slides, we say the distance from the node to the origin. So the shortest distance that we found so far is going to be referred to D, or G. But I actually refer to it as D in my representation when we do our whiteboarding. So either D of n or G of n is going to be our shortest path so far. So shortest path from source to n. And then what we end up doing basically is in Dijkstra's, we just took this d of n value and we said, let's just explore the one with the shortest d of n value. Now we're going to explore the one with the smallest value for d of n plus h of n. Why do we add d of n plus h of n here? Why does that make sense for us to explore that node first when we're finding a new node to explore? David?
Each of n is probably an easy to calculate estimate that's accurate enough to get us to an optimal solution. So now we don't have to actually calculate the actual distance of that node, right?
Sort of, yeah. So David mentioned that if we can calculate h of n, and then that tells us the remaining distance, and d of n tells us the distance we've gone so far, don't we want to calculate the one that has the smallest total distance, which is what d plus h represents? Yeah, totally. One caveat that I want to mention is David said that h of n might be an easy to calculate heuristic. That's not necessarily true. Most of the time, the heuristic is not easy to calculate at all. So for the example of Uber Pool, they're going to have a very, very complicated heuristic of how to estimate how much the rest of their distance is. However, if we have that value, then we just do d of n plus h of n, and it doesn't matter. That should be our shortest total path, theoretically. So that's the one that we explore first. So Dijkstra's is an example of a greedy algorithm that always produces the optimal results. A star is the exact same thing. A star is another greedy algorithm. So raise your hand if you remember what a greedy algorithm is. Adarsh, do you know what a greedy algorithm is?
So essentially, you are looking for optimal paths based on some sort of mathematics. So if you have weighted nodes, you would want to go for the whatever costs the least.
Yeah, and why do we go with the one that costs the least?
Because it ends up being more efficient in the overall path.
Yeah, so a greedy algorithm, to add on to what Adarsh said, is an algorithm that doesn't care about the future and doesn't care about past decisions that we made. All we care about is how to optimize what we have currently in front of us. And the reason greedy algorithms are really, really important in this class and why we're going over multiple of them is you don't need access to the entire graph, for example. So on project 2, for example, when you're implementing Dijkstra's or A star, you shouldn't need the entire graph. In fact, you should not have the entire graph passed into your Dijkstra's implementation. If you do, you're probably doing something wrong. So again, let's think about Uberpool. Like if it's calling Dijkstra's and it needs the entire graph of the entire world in order to find a path for you, then something's probably broken about the algorithm. So that's the beauty of Dijkstra's, and A star is the same thing. It's a greedy algorithm, which means you don't need the entire graph that you're looking at. You just need a single starting node, basically. And then it always produces the optimal result because of the optimal substructure. So again, we have an optimal substructure, which produces the optimal result at the end of the day when you've run A star. And again, A star is the optimal path to get to that final path. So A star produces an optimal solution. All of these are caveated with making sure that the heuristic is admissible. So A star produces the optimal solution if and only if the heuristic that we choose to evaluate our next node is admissible. If you don't have an admissible heuristic here, then everything goes to shit. We really want to avoid any type of heuristic that is non-admissible. And an admissible heuristic basically says it's never going to overestimate the true distance to the destination. In other words, an admissible heuristic tells us that the distance from A to B, basically, so D of B is always going to be greater than H of B. So D is going to be the actual true distance, and that's always going to be bigger than the value that we have H, basically. So in other words, if you have something that this is similar to life, where when a manager asks you how long something is going to take, you never want to underestimate, you never want to overestimate. You don't want to be like, hey, this is going to take me 2 months, because then people might be like, hey, that's not great. You always want to underestimate how much work that's going to take and then over deliver on it. So you always want to say like this is going to take some amount of time, and then like you want to underestimate how much effort it's going to take and then over deliver by beating that estimate overall. So if you think about a graph in the same terms, like let's say that if A is connected to B with a graph weight with a weight of 9, this is the amount of effort that it takes to go from A to B. So you always want to underestimate the effort instead of overestimating it. If you ever overestimate the effort, then A star breaks down and A star will actually fail. So you never want to have that happen, basically. So really quickly, what is the easiest admissible heuristic that we're going to have in A star? So if we say h of n equals something, and we don't know anything about the actual paths yet or how far everything is, like we don't have the entire graph yet. What is one way to calculate h of n here? Like what is the easiest value that we can say for h of n that ends up working? Any ideas? Nirav?
We can have h of n always be 1.
You can have it be 1, but that isn't necessarily going to that isn't necessarily going to underestimate, right? Because the only constraint that we have about Dijkstra's in A star is that the values are non-negative. So if we have A to B is equal to 0.5 here, then that breaks down. So Nirav, what should the value actually be here?
0.
Exactly. So we want this to be 0. And that is always going to be admissible here, always going to be an admissible heuristic if we say h of n is always equal to 0. So if we set that heuristic equal to 0, what algorithm do we have? Alex, did you have a question? Alex might be typing here. Hopefully, can you reiterate the admissible part? Sure. So the admissible part basically means that if we have two nodes A to B and their actual true distance here is going to be 10, then we want to make sure that the heuristic, or let's say we have another node here. C is our destination and A is our source. And this is 10 and that's 5, then basically what's going to end up happening here is if we say the heuristic of A, which is the path, the total edge weight from A to C is equal to 17, this isn't an admissible heuristic, basically. So if this is an inadmissible heuristic, it means that we're overestimating how much it takes to go from A to C, basically. So that's not good. We want to change this to be 12. It's basically a lower bound on the total effort it takes to go from our current node to the destination, basically. Sean, that's totally true. If you want to compare to your Fifth Avenue and my Sixth Avenue example, if my heuristic tells me that Fifth Avenue is 3 miles when the actual value is 1 mile, then we're overestimating the amount of effort that it would take, and that could be problematic, for example. H of n equals d of n minus 1. Yeah. So you can make h of n equal to d of n minus 1. However, in that example, Arthi, that means that we actually need to know the true distances. We don't know, the whole point of A star is we don't actually know those true distances. We're calculating those true distances. So that's why we need a heuristic that just estimates the true distance instead of actually knowing the true distance and then doing something with it. Because at the end of the day, what we're trying to find is d of n for nodes we care about. So the simplest heuristic that's going to end up working is what Nirav said. H of n equals 0 here. So if we have h of n equals 0 there, what algorithm do we have there? Not DFS, it's Dijkstra's. Yep. Bridge, why is that Dijkstra's algorithm? Lucky guess. Okay. Tien, do you have any thoughts on that?
Yeah, I was gonna say because we have no information about heuristic functions, so it goes back to Dijkstra.
Absolutely, yes. So if if we have no information about any estimates or anything, then all we're doing is finding a single source shortest path from a single source to the destination without any information about estimates. So that is Dijkstra's algorithm. Exactly. Great thought. Michelle, if h of n is not known, will it always be h of n equals 0? Absolutely, yes. So another way to think about Dijkstra's is that Dijkstra's is just a special case of A star where h of n is always equal to 0, correct? So does A star not stop as soon as you get to the goal state? It does stop as soon as you get to the goal state. I guess so that is a little bit different from Dijkstra's because, well, no, even in Dijkstra's, it stops as soon as you mark the goal as visited, which is the same thing that you do in A star as well. Once we get to this pseudocode and once we go through a whiteboarding example, you'll be able to see very, very similar, huge similarities between Dijkstra's algorithm and A star as well. So let's do a partner exercise real quick. So again, partner up with someone and chat with them either on here, Slack, or Discord, and talk about whether this is an admissible heuristic. So basically what this is doing is saying the value of h here is equal to 9. So just as a quick example, basically what we're trying to see is the total distance from A to our destination H less than or equal to 9, basically. Or sorry, greater than or equal to 9. Because we never want to overestimate the distance, so we want to make sure that the true distance from A to H here is greater than 9. So take a minute with your partner and actually figure out whether this is a fully admissible heuristic for all of these values here. All right, let's come back together. Dorian, what are you thinking here?
Well, the shortest path from A to H, it's 7, right? So the heuristic
So
H
where
of A from the
7?
3, 2, 1, 1, A, B, C, D, E, H, right?
So that one actually, oh, so this might be just an artifact of how it's labeled, but this is actually 8 here.
Oh, okay. Yeah, I didn't see that. Sorry.
But you're on the right track. Let's try, what about the heuristic value for F?
For F. 8. And yeah, so this wouldn't be an admissible heuristic, right? Because there's the effort is 8 to get to H, and the heuristic is 9. So
Yeah. So thank you. So the value that we have for h of f is 9. The actual distance from for d of f is going to be equal to, if we start at f and we try to get to h, we go up to b, then down to g, then over to h. So we have 1 plus 6 plus 1, which equals 8. So The distance is actually less than the heuristic value. We overestimated how much work it's going to take to actually get there, which is not good. How do we end up fixing this so that we make it an admissible heuristic? Like what value can we change this number to make this an admissible heuristic? Tian?
Anything that's less than eight or 8.
Yeah, exactly. So we can change it to 8, we can change it to 7, we can change it to negative infinity, anything we want here. The closer a heuristic is to the actual distance, the better. So 8 is going to be our best value, but obviously we don't have access to the actual distances or anything like that. So it's hard to be like, we should choose 8 or something like that. If we have some function, our heuristic function, that gives us a choice between 8 or 7, then obviously we should choose the larger one if we're guaranteed that it's going to be admissible, but we don't always have that option. So like we did already, we can just change that 9 to an 8 or a 7, and that would make it admissible as well. So let's go over what the algorithm actually is. Raise your hand if you have any questions about this example. Okay, cool. So let's go over the actual algorithm now. So Arthi?
So when should they all be 0? I thought before that we said that all the heuristics are 0.
We shouldn't always have it be 0. If h of n equals 0 for all n, this is Dijkstra's, basically. That's all I was trying to say.
Oh, okay.
So if that's equal to 0, then that it's automatically Dijkstra's algorithm, but that doesn't mean that we should always have it 0. We should try to avoid having it be 0 at all costs, basically. George?
Wait, why are we changing f to 7?
Why are we? Oh, I see. We can't really change it in a normal algorithm or anything. Like the heuristic value is the heuristic algorithm, but if we have a different heuristic now, let's call this h prime. If h prime for this generates something like 7 here, then all I'm trying to say here is that this heuristic is admissible versus the last one, which had a 9, is not admissible. So h isn't admissible because it generates a value of 9 for h of f, but h prime generates a value of 7 for h prime of f, which means that it's okay.
Wait, I thought we wanted to overestimate though, so wasn't the 9 okay?
We never want to overestimate. We always want to
Oh, okay.
underestimate that.
Oh, okay.
So we always want to say this is at least the amount of effort that it's going to take. We never want to say this is more than the effort that it's going to take to get to the distance. That's just how A star works. Yep. Cool. Should H be as big as possible without ever overestimating? Absolutely, Ryan. So we want to find a heuristic function that we can define that makes H the biggest value possible without overestimating the value that we have there. So absolutely, you hit the nail on the head. But obviously, that's not always possible. Like we might not be able to find a heuristic that gives you the maximal value every time or something. So keep in mind that heuristics are not going to be perfect. They're not going to be like the exact right value that you're looking for every time. But the closer we get to the actual value, the better without actually overestimating. So let's go over the algorithm. This should look very familiar. This is very similar to A star or to Dijkstra's. So first, we want to create an empty map of nodes to pairs of distances. So before we had a map of node to G, basically, now we want to do nodes to G and H. So G is the distance so far, and H is the estimate, like we already talked about. We want to calculate the value of the origins heuristic, so H of A, basically, and set the distance for the origin to 0, comma h, basically. So that's going to be, this is equal to g, so g equals 0, and h we end up calculating. And then we go through Dijkstra's, the same exact process. We finalize the curve, we relax the neighbors, we update their heights and do that. And then we also do this extra step here where we calculate the heuristic value and assign it to h. Then we set curve to the next minimum node, and then we set the node to the smallest g plus h value that's not yet finalized. So before we set it to the smallest g value for Dijkstra's, and now all we're doing is setting it to g plus h for a star. So all we're doing is basically changing g into g plus h here to figure out what the next node that we should explore is. And then lastly, once we have once we have visited our last node, basically, once we have visited our destination, we return the g value for the destination. Is there a reason we don't return the h value for the destination? We're never returning the h value, right? Why don't we do that? Tian?
Is that because by then h value will be 0?
So we can't guarantee, oh, actually we can guarantee that the h value is 0. So that's totally valid. The h value for the destination has to be 0 because the fastest way to get from the destination to the destination is 0, and we can't overestimate. So yes, the h value is definitely going to be 0 there. And the other thing to keep in mind is that this is just an estimate anyway. We don't need to return an estimate. We don't care about what the estimate was for whatever reason. We care about what the actual true distance was. So this is just used for this step. This is the only place where we actually use the h value. So step 3D, use h value. Other than that, we don't end up using the h value anywhere else. And that's totally fine. We're just using an estimate to figure out the next node to explore instead of actually doing anything with the, instead of returning anything using that value. Absolutely. So let's go ahead and do last week's example using a star real quick. Here we go. Okay. For those of you who didn't watch the lecture, please watch the lecture. It's not optional to watch lectures that weren't live for you guys. So make sure you watch this on YouTube. We went over this example with Dijkstra's last time. So let's make sure that we do that again this time. Cool. Now we're going to go over this example using the A-star algorithm, basically. And I basically set up these different things for us, and I want to do it in a greedy way, so I'm going to make some changes actually. So because it's greedy, we don't know what the value, we don't know what nodes are in this. All we know is that A is our source and G is our destination. So given that we have a value for A and G and we don't know anything else, I'm going to actually leave this entire array, all of these arrays, completely empty here. So empty means we don't even know that that node exists right now. So let's go into G, and we know that G has some D value, which is going to be, or we don't know what the D value of G is going to be. However, we know, and we don't know what the parent value is going to be. So let's give this a null. So null means we know it exists, we just haven't calculated the values for D and parent yet. And then the h value of G is definitely going to be 0, right? Because that is our destination. We don't even have to run the heuristic function. We know that that's going to be 0. And then we have some heuristic function. Up here, we have some heuristic function that spits out these numbers for us. So it says that if we put A as an input to this function, it outputs 10. So our output for h of v is equal to 10. And let's just say for the sake of this exercise that we know that this is an admissible heuristic. So h is admissible, so we know that these values are correct. All right, so one thing to keep in mind here is let's go ahead and go through the algorithm. So we start with d of a equals 0. So d of a equals 0, we already did that. And our goal is to figure out the shortest path to G starting at A. Same as Dijkstra's, we're going to figure out the shortest path. So let's calculate the minimum path from A to each of its neighbors. So what are A's neighbors really quickly? We have B, C, D, and F. So we need to figure out the shortest path from A to each of its neighbors. So firstly, the first thing we do is calculate h of A. So we did h of A and we set that equal to 10. A's neighbors are B, C, D, and F. So let's calculate the value for D of B. So the way we calculate D of B is going to be the minimum distance to A from A, which is going to be D of A, plus the distance from A to B in its direct line. So this is going to end up being D of A is just 0, because obviously the fastest way from A to A is going to be 0. And we add the distance from A to B, which is just 2. So we say that this is 2, and we fill that in. And because the minimum distance here is 2 and it was previously empty, now we say that the parent there, the way that we get to B in the fastest way is to have its parent, the last node in that path, equal to A. Tian, did you have a question?
Yeah. So in this ASR algorithm, we're not comparing the minimum distance. Like in Dijkstra, you'd be comparing, what you have on the board versus DB.
We absolutely are. But because this was empty, the previous distance was infinity. So we take the infinity, we say 2 is smaller than infinity, so then we put in a 2.
So technically, yeah, okay, we're still comparing. I see.
Exactly. Does that make sense?
Yep.
Cool. And then lastly, what we do is we fill in this value of h here. So we run our heuristic function on B and we see that it returns 5. So we fill in a 5 there. Everyone with me so far? Okay. And then we keep doing that. So we update D of B, we update the parent, we calculate the h value, and then we repeat for C, D, and F. So we take D of C now, and we say, what is the value of C here? And that is going to be D of C equals D of A plus the straight line distance from A to C, which is going to be 0 plus 4, which is equal to 4. 4 is less than infinity, so we set that equal to infinity because nothing existed. So now we just say, so we replace the value of D of C, basically. So we take this infinity, we replace this with a 4, and we say the parent was A. Then we fill in the heuristic value to be equal to 10. Matt?
Yeah. So a quick question: why do we have that the h of b is equal to 5?
Oh, what? Like, where are those values coming from?
No, just only the 5, because I'm kind of, because from B to get to G is a direct path is 8. And
yeah, so keep in mind that A star doesn't actually know that. It doesn't know the actual distances because we're trying to calculate the actual distances later, right?
Mm-hmm.
So in this case, 5 is just some arbitrary number that our heuristic function has estimated for the
So
final
you
distance.
just randomly choose that number.
Yeah, exactly. So
okay, I just want to make sure. I thought you were okay. That's fine.
It's not randomly. It's like there's a function that we don't know anything about that is telling us that's the distance. So Matt, like if I were to tell you it takes you 30 minutes to drive, if I say it takes you at least 30 minutes to drive from here to Philly, you'll be like, yeah, you're right. It takes at least 30 minutes, but it takes closer to 2 hours, you know?
Yeah.
So this is just a like.
Yeah, it's okay. I thought you get the 5 within the graph. That's why I was asking.
Ah, I see. Yep, that's
Okay.
super important. So
Yep.
this h value, I'll write this down. H of n does not represent true values. It is just an estimate determined somehow. We'll talk a little bit more about what that somehow means, but for now, let's just take it as granted that it just somehow gives you an estimate that is spit out. All right, and then we'll keep going here. Let's just do a few more. Actually, yeah, let's do the whole thing. So we did D of C. Now we want to do D of D, I believe. Yep. So D of D is going to be the same thing, D of A plus A to D, the straight line distance, which is going to be 0 plus 7 equals 7. So we say 7 here, A here, and then we run H of D. That's going to be 6 according to our function. And then we do D of F as well. So let's try D of F. D of F is going to be 0 plus 5, and that's going to be equal to 5. And then that's going to be, the parent is still A, and then the D of F value that's returned here is 2. Okay, so those are all of A's neighbors. So what is our next step? Do we remember what our next step is from Dijkstra's algorithm? Anybody? Tian?
You mark A as visited.
Yep, absolutely. So we take A and we say that A has been visited. Because all of its neighbors have been relaxed now. So after we relax A, what's our next step? Matt?
You want it specifically for A star or for Dijkstra algorithm?
Dijkstra's is fine.
Yeah, so we choose the least DV number of our array.
Yep, exactly. We find min DV, basically. That's what you said, right?
Sir.
Okay, sweet. So in Dijkstra's, we do that. How do we modify this in A star? Anybody remember? Sean, yeah. We add D and H and visit the node with the smallest sum. So we take the D values that we calculated and the H values and add them together. So for A, it's going to be 0 plus 10. B, it's going to be 2 plus 5. Oh, and A, we don't actually calculate because it's been visited, so we don't have to worry about that. So it's going to be 2 plus 5, 4 plus 10, 7 plus 6, infinity plus infinity, 5 plus 2. Or actually, we don't even know about this infinity plus infinity because we've never seen E. We don't know that E even exists so far. So we don't calculate that at all. And then we have 5 plus 2 here. Sorry. We have 5 plus 2, and then we have infinity plus 0, because we do know that G exists, but we don't know the actual distance there, so we can't make observations. So we have 7, 14, 13, 7, infinity. So let's go ahead and choose B, because the smallest value is 7, so we can go ahead and choose B. It doesn't really matter whether we choose B or F here, because they're tied, so we just go ahead and take that, and then let's go ahead and take 7. Let's just go ahead and take B. So now we take B's neighbors. So then all of B's neighbors are going to be, haha, no pun intended. All of B's neighbors are, not including A because we've already visited A, we have D, E, and G. So the distance to D is going to be D of B plus the straight line distance from B to D. So that's going to be 2 plus 6, which is 8. So this is going to be 8. Do we replace the existing value of D here, or do we leave it what it was before? Anybody have thoughts on that? Do we replace this value here? We leave it. Michelle, why do we leave it?
Because 7 is less than 8, and 7 is already like the lowest cost path.
Right. So 7 is less than 8 already. So like, why replace it with an 8 and take a more roundabout path than the shorter path that we found, which is just A to D exactly. So we don't have to do that. We don't have to replace it. So 8 is greater than 7. So leave existing value. Cool. And then we take E. So let's do E's path, which is going to be so D of E is going to be, oh, sorry. So D of E is going to be D of B plus E to D, the straight line distance basically. And then here we basically say this is going to be equal to 2 plus the straight line distance from D to E, or, oh, sorry. This is going to be B to E, not E to D. So B to E is going to be 3, which is 5. And there was no value before, so we put a 5 here, we put a B here, and then we say the H value is equal to 5 here. Does A star work for unconnected graphs? I don't see why not. You just start from A, and then you explore all of its neighbors. Again, you just start from the source. So if we had a X node out here, why wouldn't it work? We're just never going to see the X node, and that's totally fine as well. Cool. And then let's see. So then we've done the E value, and then lastly, we want to do the G value. So D of G is going to be equal to D of B plus straight line distance from B to G. So that's going to be 2 plus B to G, the straight line distance is 8, which is equal to 10. So that's still lower than null or infinity. So we end up going here and we say 10 here, and then the parent is B. Oops. And then the H value here is going to be 0 here. Cool. So after we're done with that, we visited all of B's neighbors. So what's our next step? I'll answer your question in just a sec, Rushali. So what's our next step after visiting all of B's neighbors? Mark B as visited, absolutely. So we mark this as visited, and then we choose our new node, which is going to be the minimum, the minimum value of, oops, the minimum value of D plus H, basically, which is going to be for the node F. So really quickly, Rushali, if the goal node is the X node, what ends up happening is we're going to explore all of these nodes, A, B, C, D, E, F, and G, and be like, have we found a path to X? If we haven't found that, then we're like, great, there is no path. We just say that there is no path to X starting at A, because we've exhaustively searched everything starting at A, and we haven't found any path to X. That example is very interesting. That's, for example, how you might see something on Google Maps. So like, if you look for biking distances from here to India, it's going to be like nothing exists. There's no path because it's an unconnected graph. There's no way to get to India via bike from here, basically. So that is possible. A star is being used by Google Maps. So anything that works on Google Maps should work on A star. Cool. So now we choose our next graph, or we choose our next vertex. So that's going to be F here, because 5 plus 2 is still the minimum value. So that's going to be 7. So we explore F's neighbors now. So F's neighbors here are going to be C and D and G. Questions, Tian?
Just to clarify, for B's neighbors, right? We didn't include A. Is that because A has been marked as visited, or is that because A was a source?
Well, it's because A wasn't marked as visited. So here we do the same thing. We're basically, we're not visiting A because going to A is going to be, like, we've already determined the fastest way to get to A. So why go back there and try again?
Oh, okay. Is that the same for Dijkstra's too?
Yes, exactly.
Oh, okay. So I realized that I just did a lot of extra for the Dijkstra quiz.
No worries. It's not that much extra effort, but yeah, that is true. Matt?
Thank you.
Sure. I have a quick question though. So for A star, don't we stop when we reach the goal? Like it is needed to visit all the nodes on the graph, or
We don't have to visit all the nodes in the graph, but we stop when we mark G as visited.
as visited? Okay,
Yes.
I see. All right.
And G is currently not visited yet, so we keep going until G is marked as visited. Make sense?
It does. Thank you.
Sweet. And one thing that we make slightly different here is basically we mark visited before we do all the, or you can do the same thing in Dijkstra's too. You mark it as visited and then visit all the other, you relax all the neighbors. So it's the same thing here. So for F's neighbors, we say C, D, and G. So we've already marked F as visited. And we look at C. So we basically say, what's D of F plus F to C, basically. And that's going to be 5 plus 6, which is 11. 11 is greater than 4, so we don't care about that, really. Then we try D of, oh, sorry. Did I do D of, I did this backwards. I'm sorry. We want to actually end up doing D of C here. And that's going to be D of F plus the straight line distance from F to C, which is still going to be 11, which is greater than our value of 4 here. So leave it. So next we do D of D. D of D is going to be D of F, which is still 5, plus F to D. That distance is 10, which is 15. Oh, wow. Sorry. I don't know how that happened. So that is still greater than 7, so we leave it. And then lastly, we do D of G here. And we say D of G is equal to F, which is 5, plus 6, which is 11, which is greater than 10. So you leave it again. With me so far? I know I skipped a little. I went a little faster on that than I did for previous ones, but we're just making the same calculation as before. So after we visit all those, we've left all of its neighbors. We don't have anything to relax. So we end up looking at the remaining nodes. We look at C, D, E, and G, which are all in our graph now. We know about all of them. And we try to find the minimum value here. So now we have E is equal to 5 plus 5, G is equal to 10 plus 0, D is equal to 7 plus 6, and C is equal to 4 plus 10. So we can choose arbitrarily between E and G here. So for the sake of this exercise, let's actually say we choose E first. So E is equal to 5 plus 5, which is the minimum. So technically you could choose G here and just be done. We mark it as visited and then we say the algorithm is done. Well, let's say we start with E just to prove that either one would work. So we mark E as visited. So then E has neighbors from E to B and G, basically. So, oh, sorry, B doesn't count here because B has already been marked as visited. So the only neighbor is G now. So if we want to do D of G, then this is going to be D of E plus the straight line distance from E to G, which is equal to 5 plus 7, which is 12. 12 is greater than 10, so we leave it. And then after we do that, we mark E as, or E has already been marked as visited. So now we choose the new minimum. And the new minimum now is going to be G. So G is equal to 10, like the D plus H value of G is equal to 10, whereas D is 13 and then C is 14. So G is the minimum value, so we mark G as visited. Because we mark G as visited, we return some value. And what value do we end up returning here? Any thoughts on that? Yep, just D of V, or specifically D of G, which equals 10. And one more thing to keep in mind here is we can actually trace back the direct path from A to G by saying, look at G and look at G's parent equals B. Then we look at B's parent, and that's equal to A. So then basically from here, we're going to go from G backwards to B and backwards to A. So we go from A to B to G basically. And that is our shortest path that we found. And one thing that's really cool is we never ended up visiting C or D. C or D are totally unvisited. We never had to go and explore them really. And that's the cool thing about A star. Those are never visited. Those aren't required to be visited or anything. And we're just done with those overall. In our Dijkstra's example, we ended up visiting C, D, E, and F. And then G was the last node we visited. That's not always going to be true, but we generally require in Dijkstra's visiting a lot more nodes than we do in A star. Liam, you can message me on Slack about that, and then we can talk offline. Cool. Jumping back into A star. Anybody have any questions about what we did? Okay, cool. Going forward, so obviously Dijkstra's is just a special case of A star where H of V is always equal to 0. So this is the same as A star basically, but it's a special case where H of V is equal to 0. We calculate the shortest path and not just the length, so we end up doing the same thing. It works for, just like in Dijkstra's, it works for directed and undirected graphs. It works for connected graphs, unconnected graphs, all of those things. And the only other constraint is that weights are non-negative here. So want to make sure that the edge weights are still not negative, because same reason as Dijkstra's, that can mess up the algorithm. And then the only reason that we would use Dijkstra's over A star is if you can't find an admissible heuristic and you need the optimal solution, basically. If you have an estimate of the heuristic, then you pretty much always want to use Dijkstra's, and that's what we end up doing, basically. So let's go back. I know we've been talking about this crazy concept of H, basically, as a heuristic. And I want to answer how we have an efficient admissible heuristic. This is unfortunately not like some easy solution that there's one thing that applies to everything. It entirely depends on the constraints to a problem, and there's no steps or rules for figuring it out necessarily. It really, really depends on the actual problem. Fortunately, there's an entire class of problems that A star can apply to that has really, really easy to compute heuristics overall. So we'll go over some of those heuristics really quickly. So let's take this as an example. So if we have our goal down here, and we have our origin up here, what's the shortest path from origin to goal where X is an obstacle? So this is a graph problem, basically, that's very common. And we say that you can only go up, left, down, or right, basically. So those are your 4 directions. You can't go diagonally. What's a heuristic that we can apply here that's really, really easy to compute to go from, for example, here to our destination? Oh, sorry, origin's up here. So let's say you want to go from here to your goal? What is an underestimation of how much effort it's going to take? Raise your hand if you have any thoughts. Sean? The straight line distance. Yeah, exactly. So let's say that the straight line distance is going all the way to the bottom and then going all the way to the right. So that's going to be 1, 2, 3, 4, 5, 6, 7. So h of this square is going to be 7 here. Now, obviously, it's going to take a lot more than 7 because we're going to have to go like this. That's going to be a lot more than 7. But we know that that is going to be the fastest way, if there are no obstacles, to go from this square to the goal. And Tien, you hit the nail on the head there. This is called the Manhattan distance. This is very, very important. This is going to be a heuristic that's used more commonly than any other heuristic. We call this the Manhattan distance, or the distance from an xy coordinate to, or let's say an x1, y1 coordinate to an x2, y2 coordinate. And we calculate that by basically saying the Manhattan distance, let's call that m of, let's just call that m. So m is going to be x2 minus x1 plus y2 minus y1. And you want to take the absolute value of both of those. And that's going to give you the Manhattan distance overall. So obviously, same exact thing here. That's what I'm summarizing here. You take the absolute value of the x coordinates and the y coordinates, add them together, and that's your Manhattan distance. That's one of the easiest and most efficient, or one of the easiest to calculate and easiest to visualize heuristics. So this is an admissible heuristic because even if there are no obstacles, you'd still have to traverse the entire straight line distance, basically. So this would always be the admissible heuristic, basically. It's always going to underestimate the amount of work it takes. Now let's do the diagonal. So you can do so you can move in many directions now. You can move this way, that way. You can go this way, or you can go that way. So what is the heuristic going to be to go from here all the way to here now? Any thoughts? No? Well, we can pretty much just go down this diagonal as far as we can, right? So we just go all the way here, and then there's no more diagonal to go down, so we just go down to the goal from there, basically. So yeah, in this case, Matt, the heuristic here is going to be 5. So this is called the diagonal distance heuristic. So you take the diagonal as far as you can, and then you keep going down, basically. You can calculate that by looking at the max of the two absolute values instead of just adding them together. So that is the diagonal distance. And then the last question that I have for us is one more partner exercise. What is the complexity of the A-star algorithm? So we talked last week about how the complexity of Dijkstra's is big O of V log V plus VE. So what is the complexity of Dijkstra's? Sean, oh, you're answering Ryan. I thought you were saying that this is a constant time algorithm, which I'm fairly certain we know it's not true. Okay, so what is the complexity of A-star? Take a moment with your partners and actually discuss what the complexity of this would be. Arthi, why is A star better than Dijkstra's? It basically gives you the shortest, it doesn't require you to visit every other node first. It lets you go through the different nodes in an order that is most optimal, basically, using that heuristic. Bridge, so what are we thinking about the complexity of the A star algorithm? Any thoughts? Do you have a mic or can you chat or no? Okay, no worries. Bridge said it's noisy, so that's totally fine. Don't worry about it. It's not the same as Dijkstra's because we actually have to calculate our h of v values. What's the complexity of our h of v value? Or calculating that? How long is that going to take? Yeah, it depends. So we have no idea what the h of v value does. We have absolutely no idea. We're going to make it, but it depends on the actual way that we calculate that. So again, we have these lines here. So we calculate the heuristic value here, and we calculate that heuristic value. Those are the different lines. And that means that your total algorithm depends on the runtime of your h of v value. And then you can actually calculate this basically using the same as Dijkstra's, but you also end up adding the heuristic values there. I'm not sure what Juan is referring to, but if you want Starbucks, go for it, I guess. Awesome. Now let's do a student teach back. Really quickly, Hasumi has been voluntold to do a teach back. So Hasumi, do you want to get started? You don't have to go through all of it. Just you can end at the heuristics part. So the actual algorithm, how do we go through that?
Yeah, do you want to go to that notepad?
Yes, I will do that. Yeah, just let me know where to go and then I am happy to help. Okay.
Okay, so we're starting at our source node, A, and we're basically going to stop until we mark our destination node as visited.
Uh-huh.
And so for each node, we are keeping track of whether or not we visited it. It's D of V, so it's running distance, its parent, and then its heuristic value. So since we're starting at A, we have to look at each of its neighbors. So that would be B, C, D, and F. And then for each one, we're basically calculating the distance of D to A plus A to that node.
Okay.
And then, so
do
we
we calculate something else while we're exploring D's neighbors?
Well, we're already given the heuristic values, right?
We actually end up calculating them once we explore those.
Oh, okay.
Yep. So we're not necessarily given them, we end up calculating them. In this example, I just gave them to us so that we don't have to worry about what the function is.
Okay, so we'll have to calculate the heuristic values as well.
Yep.
And then basically once we've looked at all those neighbors, like we've relaxed all of them, we mark A as visited. And then when we're choosing the next node to move on to, we have to calculate the minimum of the D of V plus H of V. And that would be our next node to go to.
Yep. Cool. One thing before people end up leaving that I wanted to announce, today's daily quiz is the just write down 3 questions that you might have for the industry engineers from next week. So again, that is daily quiz is 3 questions for tomorrow. And again, you don't have to come tomorrow if you're not in section 2, but that is your daily quiz homework. Just take a picture of the 3 questions that you might have for the engineers. write them down, and then take a picture and upload it to Canvas. And if you have a dying question that you really want to ask, then you can also put it in the Slido. Otherwise, we're not going to be able to answer them. So put it in the Slido as well. Will there be a write-up of the answers to the questions? I doubt it. So we might have a recording, we might not, but if you're not live, then I have no guarantees that we can answer your questions or anything. I'm really sorry about interrupting you, Hasumi. Please keep going.
Yeah, so we basically choose the minimum of D to V plus H of V, and that would be our next node to move on to. And we basically continue this until we mark our destination node as visited, and then we return the D of V, the D of the destination node.
Okay. Until G is marked visited. And then we return, what did we say? We return D of G?
Yeah,
Exactly.
D of, yeah.
Perfect, sounds right to me. And then let's go back here, and then could someone walk me through heuristics? Eric Lampy, are you still with me? Maybe not. Cool. George, are you still with me? Nope.
Yeah.
Couple. Yep. George is still with me. Cool. George, can you hear me?
Yeah.
Awesome. Would you mind walking us through what admissible heuristics are?
So it's one that always it never overestimates how far away a node is from the goal node.
Mm-hmm. And what are some examples?
Oh, okay. So if we're working in like a graph type setting, then we could use something like Manhattan distance.
Okay.
If we have the operations of up, down, left, and right, because we know the Manhattan distance will always be the shortest distance. So therefore, it'll always underestimate in that case.
Makes sense. Just like here.
Yeah.
And then what about if you can move diagonally?
If we could move diagonally, then we would have to move as far diagonally as we can towards the goal state and then move down.
Yep, exactly. Sweet. And then what is the runtime of A star?
It depends on the time complexity of that heuristic algorithm. Not the heuristic like calculation.
Yep. So it's going to be the same as Dijkstra's, but with the additional complexity of the heuristic algorithm. So it's going to look something, to be totally explicit about it, I believe it's going to look something like V log V plus VE plus V times H of V. So I think that is going to be the total complexity. I'll amend this if that turns out to be wrong, but I'm pretty sure that this is going to be the complexity of the A star algorithm. Does that make sense, everyone? Great job to George and Hasumi, who don't have to do today's daily quiz. Give them a big round of applause, basically. Shuo, yes, V is the number of vertices, basically. Cool. So the complexity is worse than Dijkstra's. Yes, it's a little worse than Dijkstra's, but at the extent where this might be a little bit shorter in reality. V log VE and VE might actually be a smaller amount of vertices and edges that we end up exploring. So yes, the worst case complexity might be worse, but the normal complexity, like the actual number of the number of iterations that we have is going to be quite a bit smaller for A star than it is for Dijkstra's. Awesome, that is it for today's lecture. Oh, Ryan, what's up?
Can you go to the comparison slide again?
Yeah. Yep.
Okay, the second point of A star doesn't make sense to me. I thought you need to have an admissible heuristic to use A star.
Okay. So this isn't that important of a point, but what this basically means is maybe you don't need the optimal solution. You're okay with like it not being great, but your admissible heuristic allows for that margin of error. So basically, let's say in Uber Pool, you don't need the optimal match. You just need a good enough match, and you have a heuristic that tells you like good enough is good enough. It still counts as an, oh, I see what you're talking about. This is worded a little badly. So it basically means that your heuristic is a good enough heuristic, which basically says, hey, this is an admissible heuristic, but it's not going to give us the optimal value, basically. It's just going to give us some value that we care about at the end of the day. Make sense?
Yeah.
Okay. Yeah, don't worry too much about this point. That's not going to come up in our class very much. TN, yes, it does always result in the shortest path as long as you have an admissible heuristic. So basically, don't worry about this bullet point. It doesn't apply to this class, so you don't have to worry about it at all. This is more of an advanced topic in computer science that we don't really care about. So in the extent of A star in our class, it will always return the shortest path with an admissible heuristic. Cool, so that is it for today's lecture. Please make sure to try to come tomorrow to lecture if you can. It's gonna be from 10 to 11:20, the same exact time. It's gonna be a guest lecture with some awesome guest speakers, and it's gonna be an open Q&A basically. It took a lot of effort to organize, but I'm super excited about it. It's probably one of my favorite lectures of the entire series. So please try to come if you can. That's also 80 minutes where you don't have to listen to me. You can listen to other people, basically. Today's daily quiz is write down 3 questions that you want to ask your daily quizzes, ask your guest speakers from tomorrow, and then take a picture of it or type it up and then turn it in on Canvas. So very quick daily quiz, and that should be pretty straightforward as well. Awesome. Thank you very much. Have a great day, and I hopefully will see all of you tomorrow. Bye.